If the universe is infinitely big, then you can pretty much prove mathematically that there'd be infinite copies of us. You can absolutely talk about this idea seriously. Sure, maybe the Big Bang is an interesting event, but not the beginning of time. But maybe the universe existed before that. Maybe there were other Big Bangs that happened before that. Maybe there's a whole prehistory leading up to the event that we call the Big Bang. You can't have physics without general relativity and quantum mechanics playing well together, as string theory is still the most promising approach.
Host of the interview is Dr. Matt Kawecki, a science popularizer and a former digital ambassador of the European Union.
What's happened before Big Bang?
No one knows what happened before the Big Bang. No one even knows if the concept of before is relevant when you apply it to the Big Bang. I mean, before obviously is relevant to what was I doing before I got here today, or what was I doing before the election, a couple of weeks ago. All those notions of before make sense. But the Big Bang may be the moment where time itself began. And if that's the case, to talk about before the Big Bang would be to talk about a time when there was no time. And so it'd be an incoherent notion. That's one possibility. The other possibility is, sure, maybe the Big Bang is an interesting event, but not the beginning of time, not the beginning of everything. Maybe the Big Bang is an interesting realm in which the universe swelled rapidly. That's what we mean by the Big Bang. But maybe the universe existed before that. Maybe there were other Big Bangs that happened before that. Maybe there's a whole prehistory leading up to the event that we call the Big Bang. As of today, nobody knows which or if any of these perspectives is correct.
Did time have beginning?
Did time have a beginning? Nobody knows. In our theories, mathematical theories, we always assume that there is time from the get-go. We don't even know how to formulate physical laws without assuming that time exists. So our mathematics gives us no insight into whether there is an origin to time or whether there might even be a realm where there is no time, there is no space. And only when the ingredients in that realm that we can't fully describe, when they arrange themselves correctly, then space and time as we know them emerge. We don't know if that's a sensible way of thinking about reality, but it certainly is a compelling one to imagine that as a possibility.
Maybe time is the illusion of our brain, of our mind.
Time could certainly be a human construct. Time could be something that we impose on the external world because it allows us to organize events. And when we can organize events, we can find coherence, we can find patterns, we can describe it all mathematically. But sure, can I imagine that we encounter some alien civilization in the far future and their conception of reality doesn't involve time at all, or maybe as fundamentally as our conception does, that they organize events according to a completely different framework that does not involve moment after moment after moment, that their experience is not felt as moment after moment after moment as our experience is? Can I imagine that? Yeah, I can.
Did universe begin from something small like a pin? Is it possible?
Sure. In the conventional approach to the Big Bang, which often goes under the name of inflationary cosmology, we imagine that there was a little tiny pea-like sized part of space that was filled with a certain kind of cosmic fuel. It's called the inflaton field. Name doesn't matter, but this fuel gives rise to powerful, repulsive gravity. That's a weird idea. We are used to gravity that's attractive. You drop something, it falls to the earth because the earth and the object attract one another. We have never directly experienced repulsive gravity, but Einstein's equations from general relativity say that it is real, that it does exist. And so imagine you have a little pea-like shape that's filled with this fuel that gives rise to repulsive gravity, causing it to rapidly swell, to blow apart. That's what we think may have been the Big Bang. And so yes, everything would have started from an incredibly small but dense, highly energetic starting point that gave rise to the Big Bang. we can use the inflationary theory together with our understanding of the electromagnetic force and the nuclear forces. We can use powerful computers to simulate what the universe will look like after this rapid swelling. And we understand the formation of stars and galaxies, not in every detail by any means, but we can understand the processes well enough to get a sense of what the universe should look like on its largest of scales. And amazingly, while we don't have all the details, what our computers predict is pretty close to what we see. And that's an amazing achievement.
Cosmological landscape changed your life?
Well, all of these ideas have changed my life because my perspective is guided by my understanding of reality. And so as I learned quantum mechanics, my sense of reality began to shift. And so and my engagement with the world began to shift. When I learned the general theory of relativity, the same thing happened. These were wondrous educational moments for me. It wasn't just learning about warps and curves in the fabric of space. I felt like I knew the universe better. I understood it better. I could engage with it more richly. And sure, these more speculative ideas that there might be other universes out there, does that change my view? It enriches it as a real possibility that this reality might be one of many. How could knowledge of these ideas not then back react on your own view of who you are and how you fit in? It does.
Infinity universes, do you believe that it could exist?
I think the possibility of infinite universes is an idea worth having in your toolkit because A, it naturally emerges from a variety of ideas, from the inflationary theory to the many worlds interpretation of quantum mechanics, so it may be true. And if it is true, it completely changes the landscape of reality. And so for me to sit here and imagine there might be a copy of me out there in the cosmos.
Somewhere there, infinity copy of us.
If the universe is infinitely big, then you can pretty much prove mathematically that there'd be infinite copies of us out there, one after another, sometimes having exactly the same conversations, sometimes having slightly different conversations. That's a crazy idea.
But is it the idea or theory, real theory?
You can absolutely talk about this idea seriously if you're willing to make an assumption. And that assumption, you should realize, could be wrong. The assumption is, does space go on infinitely far? Or could it be that you go out sufficiently distant and you maybe circle back to your starting point, as would happen on the surface of the Earth? We don't know the answer, but under the assumption that space goes on infinitely far, you can argue convincingly with mathematics that there would be copies of us out there.
Infinity universes can be connected with our universe?
Connections between the different universes depends on the flavor of the multiverse that you look at. If you're thinking about an infinitely large universe, then yeah, in principle, you could start here, and in principle, you could pass through those universes if you had enough longevity and if you could travel fast enough. But there are other versions of infinite universes, such as that from quantum mechanics, where you really couldn't jump from one universe to another. That's not the way that version of the multiverse emerges. So it's completely dependent on the flavor of multiverse that you're interested in.
26 years ago, your bestseller, Elegant Universe, was published. You spent so much time string theory. Today, when I'm talking with scientists, they mostly say it's a beautiful mathematical idea, but it doesn't exist. We have no proof. And on the Washington Post, your last one article that we should still conduct research regarding string theory. Doesn't matter that we have no proof. Why? Why you believe still that string theory, it's a serious theory that we should be focused?
So I would agree with all of those that you make reference to.
You agree?
I agree.
You
with,
agree?
I agree with all of those who you've made reference to, at least if your summary is an accurate depiction of the perspective. I agree that string theory is a beautiful mathematical structure. I agree that there is zero experimental or observational data establishing that string theory is the correct theory of the universe. So what do?
And it doesn't work when we have more than 11 dimensions.
And the theory absolutely requires that the fabric of space be far more subtle and rich than Einstein himself or Newton would have thought. The possibility of extra dimensions is a natural consequence of string theory. All of this is true. Nevertheless, string theory does have the capacity to describe the world as we know it. Is it the right theory? We don't know. And so as the most promising approach that we have yet found for putting Einstein's ideas of gravity together with the laws of quantum physics, a union that has to happen. You can't have physics without general relativity and quantum mechanics playing well together. As string theory is still the most promising approach, of course we should pursue it mathematically, vigorously, seeking to extract some observation or experiment that maybe one day we can carry out. But as I said in the Washington Post article, if somebody comes along tomorrow and shows that there's a mathematical flaw in string theory, we should abandon it. This has never happened. If tomorrow somebody should come along and say, look at this new idea that we can put general relativity and quantum mechanics together and it's immediately close to the world and we can test it. And let's go. Of course I'd be excited and I would jump at that possibility as a new direction to pursue. So I'm not sitting here dogmatically saying string theory. No, not at all. I'm saying truth. Let's try to find things that take us closer to truth. At the moment, that is string theory in terms of putting the laws of physics into a unified framework. But is it possible that we'll have something else? 3 years, 5 years, 100 years? That string theory will be relegated to the dustbin of science? Is that possible? Of course it's possible.
Maybe Twister's theory will replace string theory.
Look, Roger Penrose did a remarkable job.
6 years old theory.
Yeah. So he did a remarkable job in developing the twister idea. And there's beautiful mathematics within twister theory. And in fact, there are subtle ways that the twister idea has been in dialogue with string theory. It's not as though these ideas are at opposite ends of some kind of theory spectrum. And so, yes, is it possible that there's some deep truth in Roger's approach? Yes. Is it possible that there's some deep truth in the string theoretic approach? Yes. How will we figure it out? Continue to work, to develop the equations, develop the mathematics, extract whatever insight we can into the theories. That's the only way to answer those deep questions.
Do you believe that we'll ever find the answer what connect quantum world and classical reality?
That is a big question.
The biggest?
Well, yeah, it's among the biggest questions. How to go from the quantum description.
From the chaos on the quantum level to the Newtonian reality.
Yeah, I mean, we're still struggling. Even, and this is an important lesson, we're still now struggling 100 years after quantum mechanics was written down by Heisenberg and Schrödinger. This is 1925 and 1926. 100 years later, we can use the equations to make predictions that are borne out by experiment. We can use the equations to engineer things like integrated circuits, making everything from, cell phones to laptop computers that have revolutionized life on this planet. And yet, even with those successes, there are deep questions within quantum mechanics that we've yet to resolve. And the biggest one is, how do you go from the quantum description of a reality that is described as a fuzzy haze of probabilities, which is the language of quantum physics, how do you go from that to the definite reality that we all experience every moment of our lives? What's the transition from the quantum to the
How
classical?
matter is transformed from the quantum world to classical reality.
Yes, that's the deep question. Now, there are many physicists who think that's a non-question. Niels Bohr, founder of quantum mechanics, thought that was a non-question. He said, you're thinking about things wrong. You're stuck in an old mindset. The new mindset, Bohr said, is you have a realm of classical equipment, and that's the stuff that we see in laboratories, and you always use the classical language to describe those things. And then when you're talking about the molecules and the atoms and particles, you use the quantum language only down there. The problem with that perspective is that the equipment is made of the very same ingredients that you use quantum mechanics to describe. It's made of the electrons and the protons and the neutrons. And so if quantum mechanics describes the ingredients in the equipment, then it must describe the equipment, which is nothing but a conglomeration of the ingredients. And it's that step that Bohr would somehow resist, and it's that step that we are still struggling to understand.
Quantum mechanics is for you local or non-local?
Quantum mechanics, as far as we can tell, is non-local. And this is one of the deep insights that came from the work of John Bell, working in the 1960s, a name that most people have never heard of. Everybody knows
But
Einstein.
should.
They should, because it was John Bell, almost as a hobby. He was working at CERN, particle accelerator, was working on other things, but in his spare time, liked to think about the foundations of quantum mechanics. And in his work, he was able to reveal a test to determine whether or not certain ideas that Einstein had, that the universe was local, what you do here only affects things here, and that it was real, that particles always have definite features. He came up with a test of Einstein's view. Nobody thought you could test Einstein's view. It was just metaphysics, ideas. Go away, Einstein. You're just thinking philosophy. We're physicists, which is basically what people said toward the latter decades of Einstein's life. But John Bell said, no, this is not just philosophy, this is physics. We can actually test whether these things Einstein was saying are true. And when the tests were done, they, to most people's satisfaction, revealed that Einstein's view that the universe was local, that was not true, that the universe is non-local. In a sense, what you do here can, in a very specific quantum way, be connected to something that happens over there.
If you could find just only one answer for just only one question about the reality, what it would be?
I would like to understand the nature of time. Is time something that we impose from our minds, or is it somehow intrinsic to the structure of reality? That would be one big one, but if you let me even dream even bigger, the biggest question of all is, why is there something rather than nothing? Not empty space, nothing, but why is there anything at all? Logically, you could imagine the absence of space and time and matter and energy and everything. What brought existence into being?
But outside the universe, there is nothing.
We don't know if there's even a notion of outside the universe.
The deepest unresolved question at the heart of quantum mechanics: how does the probability quantum haze transition in the defined reality of everyday experience?
Yeah.
Could you answer for that question?
I don't know an answer to that question. That is the question that we were discussing before. What is the means by which a description of the world in terms of probabilities turns into an experience of the world that is absolutely definite? How does that transition take place? We've made a lot of headway with ideas of so-called decoherence and things of that sort, but in terms of truly answering the so-called quantum measurement problem, nobody knows the answer.
What are you doing now? Tell me something about your actual research.
Yeah.
What are you doing now at Columbia University?
Yeah, so right now with a number of colleagues, we've been studying the possibility that the extra dimensions might have yet weirder properties than...
Your mind is dimensional. You are still thinking about dimensions.
Yeah, we're certainly still thinking about extra dimensions. The possibility that the extra dimensions might allow you to circumnavigate them. Maybe the extra dimensions is a large circle, a shape that you can fully transverse. And the reason this turns out to be interesting, we found that in these possible scenarios, you could send a signal from here to someplace far away, and it could get there faster than the speed of light. Faster than the speed of light.
It's impossible.
That's what most people would say, and that's what we thought too. But it turns out if you send the signal...
Einstein said that it's impossible.
Yeah, so
the speed faster than light doesn't exist.
So we're completely compatible with Einstein because locally, the speed of the signal is always equal to light speed. But if you have an extra dimension, there's two trajectories to go from here to here. There's the direct one from here to here, but there's the indirect one where you spiral around the extra dimension and get there. You would think that spiraling around would take you longer, but it doesn't. Even going at light speed, you can beat the signal that goes from here to there directly, effectively sending a signal from here to there at faster than the speed of light.
It's just only that theoretical research.
Everything I do is theoretical. Everything I do is mathematical. And so yes, this is under the assumption that there's an extra dimension in the shape of, say, a circle. It's also making the assumption that we live on a so-called membrane in string theory that's moving along this extra dimension. There's a whole set of assumptions, but remarkably, with those assumptions, you can send a signal from here to there at faster than the speed of light.
Do you believe that we can ever achieve something called AGI, strong AI, superhumans AI?
Without a doubt, I believe that. There's no obstacle fundamentally to the capacities of these artificially intelligent systems. Look, I don't think there's anything special about the biological brain that gives rise to consciousness and intelligence. I think that if you were to engineer a version of what's inside of our heads in silicon, that in principle it could think and feel and be intelligent, and there'd be nothing in principle stopping you from cramming information and capacity and chips and circuits that will allow that artificial structure to operate at a level that's beyond our capacity. So do I think that we will get there? I do, and I don't think it's far away either.
Yeah, it's for you something more than just only statistical.
Look, the approach that the large language models have been following is certainly one way. It is a statistical approach based on large data sets. But that's not the only way that researchers have been and will continue to try to achieve artificial general intelligence. You could couple those statistics with some model of the external world, with some understanding of the fundamental laws of physics, some understanding of what we have already learned in a very concrete framework. That additional structure by itself, in principle, could allow the probabilities to get you to results that are more relevant, more insightful. And so that would be a more intelligent system compared to one that's based purely on the statistics. And that's merely one approach. You've got some of the most creative thinkers in the world that are researching ways to make these systems ever better. And I don't see any limit to what it is that they can achieve.
A lot of people think that even our language, it's not enough to describe what we created, because AI, the word AI, it's not artificial, it's real.
Yeah.
We have also not one artificial intelligence. We have archipelago of islands that, of course, we integrate each other, but still there is not one continent.
Yes, I fully agree. The whole notion that intelligence can be organic or artificial is itself an artificial distinction, right? You have systems that can take in information and produce useful information as output. And whether that system happened to emerge through the ordinary biological process of a living system maturing or through some system that we build, well, it doesn't really matter. In the end of the day, it determines on input versus output. And if you can build some system that is intelligent, it is a new kind of intelligence, not necessarily an artificial version of intelligence.
I have two final questions to you. The first one is about your own Congress, World Science Congress. Why you founded that?
World Science Festival.
Yeah, why Science Festival?
Well, way back when we began the World Science Festival, we recognized an opportunity to get people excited about forefront ideas in physics, in mathematics, in computer science, in cosmology, in chemistry, and biology. And so we said, why don't we create a gathering place where we'll bring the world's leading scientists to be in direct conversation with the general public. And so this idea caught on. And at our first gathering, we had 120,000 people come to the events. And so we recognized that we had really tapped into something that mattered to people. And so we've been pursuing it ever since.
Who today inspired you the most? Who was your master? Your father, a musician?
Yeah, my father had a profound impact on me.
And today?
Well, my dad was a musician and a composer who did not have even a high school education, but was deeply interested in the world. And he was seeing it from the perspective of art, perspective of music. And that inspired me that there are so many different ways to understand reality, and each of them gives you new insights. And so that's why I don't spend my time just doing physics per se. And I think my father's influence is a big part of that. I want to understand the various ways of seeing into the workings of the world, be it from art, science, literature, music. All of these provide a more rich engagement with reality.
Thank you for your time.
My pleasure. Thank you.